Okay, so what we have here is a t by 1 vector. Okay, so what's the first guy? So the first guy here is nothing else. We take the expectation over I, so it means like, okay, take the value-weighted return of the first stock times the excess returns of the first stock for t is equal to 1, yeah, for our first observation, plus the value weight times the excess returns of the second stock given time t is 1, and so on, until we end up with value weight for the nth stock times the excess returns of the nth stock given time t is equal to 1. So we do this procedure here for each point in time. We always take the value-weighted return across all stocks, for each point in time. This is how we construct this capital Y lambda vector. So the dimension here is t by 1. Okay. Let's take this away. So obviously, for each point in time, we have a different vector of excess returns. Okay, so we have obviously for time t is equal to 1, we have a vector of excess returns across all stocks. Yeah. For time t is 1. Yeah. So this vector here has a dimension n by 1. Yeah. And for t is equal to 2, we have another vector of excess returns. It has the same dimension, n by 1. Yeah. So but it's a different vector, obviously. Yeah. That's the cross-sectional vector given time t is 1. Yeah. This is the dimension n by 1. But here in this case here, this vector has dimension t by 1, because we take across the time dimension the expectation across all stocks for each point in time. This is basically what we stack in here in this matrix vector. So next we define a new matrix X, and we call it X lambda. Okay? So X lambda, and we define X lambda as we have a vector of 1s again in the first column, and in the second column we put in this vector here that we have already estimated previously. Okay, so we grab this vector, put it here. So we have these betas, obviously, that we estimated, beta 1 there, or this beta, we have denoted it as beta 2, right? So beta 2 given time t is 1, given time t is 2, and so on and so forth. The last element is beta hat 2 given time t is capital T, as we see here. So this guy here obviously has the dimension t by 2. Okay? So now our vector lambda hat that consists of the risk premiums, we can estimate it as x lambda transposed, so we transpose this matrix here, times itself, times x lambda, inverted, times our vector y lambda. Yeah? So and obviously, what will come out here is a risk premium 0, let's call it lambda 0, and lambda 1. Okay? So it's a 2 by 1 vector. What we get here is a 2 by 1 vector, which consists of our risk premiums. So obviously, if the cumulative path returns have an impact, or if they basically predict average returns, because this is basically what our lambda vector is telling us. So if the cumulative returns, if the variation in cumulative returns predicts average returns, and because here what we have here is obviously our average returns across time, then our lambda 1 would be significantly positive, right? So this is basically what we are interested in here, in our univariate cross-sectional regressions. So how can we check if this lambda 1 is significant?